Welcome back to the Industrial Vision Days, second day of Vision. We have three presenters with us already. They are going to talk about processor technologies and smart cameras. And a very warm welcome to my first speaker, Oliver Hälsle from HEMA Electronic GmbH. And you are going to talk about the fast lane to vision electronics, modular design in hardware and software. Oliver, I look forward to your presentation. Thank you.
Thank you. So, everybody can hear me? Okay, makes sense, perfect. So, I want to tell you about what we think about electronics design in the context of embedded vision and vision applications. The fast lane to vision, the topic is, of course, that is fast, and how do we reach that? Modular design is one of the possibilities to speed up design. So, maybe some of the topics that I explained today are not brand new for you. Maybe you had some of these ideas too, or are already acting like this. So it would be interesting. You have the option to ask questions after my talk. So to see what are you already thinking or doing in that direction to speed up project management. My name is Oliver Hälsle. I'm the CEO of HEMA Electronics. We are a family-run business with 46 years on our history line. So, to get a rough idea about HEMA Electronics, we do hardware, software design and production of electronics, of hardware, FPGA-based video management. So, we do engineering. That's okay, many of you do the engineering, software development. What makes the difference about HEMA are 3 points that I want to point out on you. Is the focus on embedded vision video management. So for all of you, you know the video systems, you have sensors, you have cameras on the one side, you have a kind of processing unit, might be an industrial PC, might be a FPGA, GPU-based system, and on the other hand, you have displays or, in the future, technical systems with more or less AI to get the results and to handle these results and do whatever automation or other application is needed. So we focus on the embedded vision. So the next point that makes the difference is that we do the design, production, and product lifecycle management. So we care for the whole project. And the third one is, and that's the topic of today, we have built a platform to make it reusable, so to speed up design and to save on our resources on engineers. So maybe you will see in this slide that you know the situation. Yeah. Daily life of engineers, it's typical at our company too. We are not different than our customers or partners. All the projects that you are integrated part of the team, you have stress, you have frustration, you have long working days because the project started too late. That's typical. And who has to do the final engineering task in the last couple of days or nights? Yeah, you began too late. You have to run for your life to solve the task at the end. It's the engineers. Yeah, on the last day. And the next project, it's the same. You didn't learn, or the organization didn't learn because it starts too late again, and you have to run at the end. Yeah? And you are not really happy. So what do we do with these results that we see for many, many years in our history with our projects and our company projects? And when you are proud to reach the results at the end, somehow is meant by out of time, out of budget, and out of your own expectations because it went not as you would like to have it. It was not agile, it was not flexible. So this is the situation on project management that we face often. Yeah? Maybe at your projects too, Sometimes at ours, yes, it is like this. So when we have a design project, when we design electronics, embedded vision electronics, to support a sensor system, a whole automation system, we have several possibilities to design the system. Often, we can pick a component from the shelf. We can use an industrial PC, we can buy a component, an accelerator card, we can use a server infrastructure from HP, a whole rack, something like that. We can buy the components. On the other hand, we can build them from scratch. So if you don't have a component available, you can build it from scratch. Nice project. It's where the heart of the engineers is really belonging to, because we can deep dive into technology. Yeah, great feeling, great task, great topic. But you have to do it every time, again and again. And one of our ideas was, how can we modularize it and not do it again every time? So how can we modularize it, scale it, build building blocks out of these recurring tasks that we have? Because when we have video inputs from cameras, we have all of these projects have more or less the same kind of video inputs. So we repeat and repeat and repeat the tasks. So how not modularize it and make this easier? So to give you an idea what we think about a possible solution, that's what I meant about maybe you have the same ideas and you will find the same ideas, or you find some new ideas, or afterwards you have some ideas that would fit to our model. So we have the idea to explain how we handle these tasks. So we have defined 3 levels of technology in these kind of projects. Of course, we have hardware. We need a hardware, we need a PCB, we need a processing unit. Could be an FPGA, could be a GPU, and a smaller or bigger one, hardware level PCB. We have a second layer where we have all this IP core application driver level of software to have an image pipeline, or we have drivers for Bluetooth because we want to have a wireless transportation of our data. And the third layer is the application layer, where all these AI applications are running, where the algorithms are running, neural networks and stuff that are in these layers. That is the first step to separate the different tasks and to talk with the customers who's responsible for what kind of tasks and applications. So you get a rough idea to have several layers. So in this slide, you see some more details. You will recognize the interfaces. I hope you can see the smaller ones. Yeah, looks big enough. Typical interfaces, storage, processing, power management. That are the tasks that you, when you look at your different projects, repeat and build in more or less the same kind every time in your project. On the second level, IP cores, signal processing. You have to handle the video streaming, compression, image upgrade, image processing. It's repeatable often. Maybe there is a bigger change in these kind, on this level. It's a bit different, but there is a lot of tasks that you repeat again and again. Of course, there is already mentioned the topic of IP cores, that you can buy some of these applications already. Software application level layer 3, yeah, that's what we focus less, because that's customer specific, and mainly that's the key competence of our customers. So we build on level 1 the video units, the hardware, on level 2 the IP cores, and application is mostly done by our customers. Oh, how does that look like in the next step? So we have 45 plus modules, we call it building blocks in software and hardware. And it's, if you make just a list of it, you said, okay, what will happen in a video unit? We have camera inputs like an SDI or a MIPI. You can list all these Yeah, that's part of your daily business. But we made a list and we talked to our customers what is needed again and again and again to start this kind of modularization. And in the middle of the unit, you have processing power. You have an FPGA, different kinds of, but it's the same. It's an FPGA, it's power management. So we just took a piece of paper and wrote it down. Next level, of course, when we know that we need these modules again and again and again, we said, okay, why not take the bill of material, the schematics and the layout to be repeatable, to build building blocks that reuse your parts. So an interface like a MIPI, you have a connector, of course, and depending on the functionality, you have some other components. But the tendency, it's the same. It's every time the same components. So you have the bill of material repeating the schematics and the layout. And then it looks like this. You can define with your customer the system that he wants to build up, and he can build like Lego blocks. You can take the different blocks and set up your system to see what is needed. And you see on the right side the layout, it's the same. Yeah. And even the components are the same. And as we produce the electronics, we have these components in stock. So when you go through a whole process of engineering and producing the PCBs, there's a lot of aspects that you can coordinate to streamline it and to build in a rapid succession these kind of repeating, more or less similar video units. That's the graphical visualization that one of our graphics guy did. We call that fast lane. So everything that I talked about, the modularization, the repeating tasks, and the kind of idea to make it like building with Lego, you know, to have all these modules and to reuse them, and then to speed up. That's how we present it to our customers, or I present it today to you, to say, okay, it looks like this. Most of the points might be known to you, or you have the same ideas. So the difference is that we began 5 years ago to build the company around these kind of processes. So we defined our processes to handle this fast lane aspect. Again, it's not magic. Yeah, it's just thinking, sit down, think, what do we do and how can we do it better and faster? Because there are tons of good engineers in the world. Our engineers are not better than the engineers at our customers. Yeah? But when we can help them to speed up their projects, they have a realistic chance to be number one as innovator in the market. So it's time. Yeah? Of course, a lot of people can engineer it, but if you find ways to make it faster, it really gets interesting. So on the one hand, we have to handle the growing complexity. We have engineers that we get from university. They don't have 10 or 20 years experience and can do that even while sleeping. So when we can modularize it, we can give it to new engineers, new people that can join our task forces. We can give them a system that they can use with less experience than before. Design risks are minimized. Time to market, that's what I said about. And the modularity. Because when you build a carrier card and use a system on module, FPGA module, or a GPU with like NVIDIA Jetson, you can exchange them. You can make hardware upgradable. And you can even take the carrier card out of the system. You have 6, 8, 10 weeks to redesign the carrier card. Then you can make even the carrier card upgradable in the process, while engineering, or even when the project is out at your customers. So the modularity helps a lot when you turn the company, the processes around and streamline it according to these processes that are needed. So A and B. A, you can advance engineering because you can take these cards, start engineering on day one. You have a hardware that is industrial grade level. You don't have to take evaluation kit from the companies, but you have an industrial level video card, and you can start engineering. And because you have the same FPGA like your serial product, the software people can begin from day one to build their software on a serial near FPGA platform. Number B, option B is you don't take the existing card, but you take the 6, 8 to 10 weeks to build your own prototype hardware in that early stage. So there are different ways, or even more. I think there are more options to use this kind of platform to speed up engineering, especially in the beginning, and to be way more flexible during the design process, because you can iterate embedded hardware much, much faster, and you have several steps, and you can go into testing, serial testing, much earlier, and test your system and make changes, so you don't have to wait 4 to 6 months for the new PCB. That makes the difference in our point of view and with our experience. So, come to the end. What was important for me to tell you about our experience and the ideas that we got from discussions with our customers, from project experience, and the ideas, maybe similar ideas like you have, and how we turned the company around to make it real, to act like this. And that is the thing that I want to present you, how the company should change, not only have the ideas, but how you have to push them through to the whole company, from design to production to engineering, and to the people and the heads and who build the strategy, and to change this. So that is the idea. What we say, we effectively support our customers in being tomorrow's world market leaders. And the focus today for my discussion was effectively speed up, make it easier and faster. And maybe there is a little bit of HEMA Visioneer spirit inside of your new project. Maybe we can support you. I hope there will be some discussions afterwards. I think my time is over, and we have time for questions right now. Thanks for your time.
Thank you, Oliver. I could allow one question. Is there a question from the audience? Yeah?
Thanks very much. Very insightful presentation. I was wondering how you sort of add the idea of design for manufacturing in this rapid prototyping that you were now emphasizing on.
Design for manufacturing was...
For higher volume. So once you go then beyond those 25, 30 days, which is your sort of your development cycle, once you need to truly scale up in order to have cost down and higher volumes, yield, and all these considerations, where in this equation sort of this factors in? Okay,
so when at the beginning you have only prototype status, so you need some of them. And if the idea is really good, we have to scale up. So at first, at the beginning, it doesn't make a big difference, because we can take the platform and start programming, start engineering. And then depending on these first prototypes and the engineering and testing, and sending your salespeople out there to present it, yeah, then you get a market feedback in what kind of application we can go and what numbers do we get. And then we can go into several directions. Of course, we have a low volume, high power application, so we can ramp up, we can exchange the system and module FPGA to have a more expensive, but of course more powerful version. And we can shrink down the components, so we can exchange the components in a next design run to scale down on, of course, the expensive components like the FPGA. We take a smaller one. Or if we go in high volumes, we can go into a design in. Then we just shrink it down and buy less expensive components like connectors. Yeah. Connectors are very valuable components, and the FPGA is important. And then we can iterate down from this status of working prototype. Yeah. And of course, if we manage to stick more or less to the same components, we have a same component strategy, what makes it easy to build and manufacture the high volume, low cost and the high volume with more or less the same components, so we profit from the high volume and the low volume, and we can build a kind of family of products that have different applications and different cost factors. That's the idea that follows afterwards. Yeah. Thanks for the question.
Thank you, Oliver. So, Oliver talked about how to speed up your development, among others. My next speaker is Ruven from Gidel, and Ruven is going to speak about how to boost your system performance. So, Ruven, the floor is yours.
Thank you. Okay. So, hello everyone. My name is Ruven Weintraub. I'm the founder and CTO of Gidel, and I have about 40 years of experience on accelerating platforms, and I want to share with you some of my knowledge. Who of you have heard about algo trading? Okay, so algo trading is in the stock exchange, where computers are competing to buy and sell. Back in 2007, I met people, and for them, 1 millisecond worth $100 million, because there's no second chance. You have a computer, if you bid first, you get the deal, and 1 microsecond later, no deal. Okay? Then, about 10 years ago, and of that time, everybody works only with the C, and there's regulation, and people told me no way FPGA would be in the market for that. 10 years later, the pricing was dropped only to 4 million, but 4 million for 1 microsecond. At that time, if you're not in the FPGA, you're out of business. And I was so surprised to see IT manager of one of the biggest banks in the world, and he was so experienced about what FPGA is doing, and more important, how we can get a lot of FPGA designers at a lower salary rate. That's already what he told me. So going back to our need, boosting the performance. So the first question is, what is performance? So for some people, performance is the throughput, which is actually combined from 3 elements. And what we see today is that these 3 elements are getting bigger and bigger in each one of them. We have higher camera resolutions, we have higher frame rates, and we are using more and more cameras, so the throughput is coming really essential to accelerate. For others, the latency, like in the algo trading. Others may be accuracy and detectability. To be more accurate or to be more detecting can be relevant. Maybe you need to be on a drone and then the weight is more crucial, or you need to be within a small environment and then the size would be crucial. And of course, thanks Oliver, concept to market may be crucial to others, and maybe several of those. So the first thing I would say is to analyze what is your need to accelerate performance. And then, for example, with the latency, some people are saying, let's say a doctor needs to do a surgery, and you used to work with 20 frames per second, and you know you need to have 2 frames or 1 frame latency. Now you're working with a 60 frames per second, and some people are saying, okay, let's have 2 frame latency. But the actual performance you need is still the same time, because the reaction of the doctor is the same time. On the other hand, as we saw in the algo trading, the latency dropped down severely. Okay, so understanding what you need. Another thing is alternatives. For example, accuracy. We all talk about AI. A couple of years ago, not so far away, everyone worked at floating point for AI. Then Google came and said, you know something? We can work at 8-bit and lose only 1% of accuracy. But the fact we are working with 8-bit enables us to have a lower cost impression and to have much more logic. And maybe with that, we're going to get, with additional layers, we're going to get much better system. So these are elements to understand about the different options and capabilities that we have. And I think a very important thing is to understand that we all care about accuracy, but sometimes we exaggerate with accuracy in one point and we lose other elements, including accuracy, on another point. And therefore, I think taking back what you need and think, why do I need it? Why do I need this performance? Why do I need that performance? And then we can realize where there's another way, there's another alternative, maybe to solve it better. And here's just some of the bottlenecks that can appear in all kind of systems. And if I'm focused just on the processing for now, then you can select the AI engine, GPU, CPU, FPGA, and so on. So first of all, I'd like to say thank you for Oliver, because I do believe strongly that the modularity is crucial with today's market. And also sometimes we want to accelerate our performance, but we are not sure what exactly the customer will ask. And also with the large quantities, what Oliver pointed out is you start with the small things, you feel the market, and then when you want to make the quantities in production, you know exactly what to do. So in that case, you can combine the two things, the low cost as a production, but the fast time to market, the fast reaction, and so on. So, as I told, I strongly believe in the hybrid computing. There's things that are better to do in the AI engines. GPU, obviously, everyone knows about them, and there's things to do in the CPU. And as Oliver said, definitely the FPGA processing is something that can accelerate a lot, reduce power, and today it's not so expensive. You talked about the pricing and so on. I remember about 14 years ago, I went to a customer and they purchased from us FPGA board that cost $10,000. And he told me, you see, the computer is $40,000. Your board is only $10,000 and it's doing 80% of the job. Okay, so when we're talking about pricing, it depends on the systems and so on. Obviously today the FPGAs are much cheaper and Oliver knows it very well. So here's an example where I believe strongly, and that is if you take the number crunching and use that in the FPGA, such as the histogram, so running the data and making a table, this is a pure number crunching job, and that the FPGA can do very fast, and you don't care about latency and things like that, and also very accurate and low power and so on. But analyzing the table, this sometimes is very simple. You want to know minimum, maximum, fine. But if you want to look at specific angles in order to know exactly how to map your gamma corrections, to tailor it exactly to the scenario or to the image and things like that, this is a task for a CPU that can do a very good random thing. So going back to Oliver's concept of modularity, from my perspective, to have the FPGA IP with a CPU software that complete it as a full class, this is a module. So with the Gidel technology, we can use these kind of modules and combines all these modules in the applications. Moving into an example, okay? What you can see here is a HDR example. In the HDR, many cameras are doing HDR in two ways. One way is two exposures, a high exposure and low exposure. This is excellent because they can get a good image in both cases. However, there's an issue. What is the issue that they have? Frame rate. And today, the market demands a lot of frame rate. So if you can get one frame and get HDR out of it, it would be good. However, if you look at the image, on the left-hand side, the original image, some of the data is very dark. It's in the shade. Some of the data have a direct sunlight. It's very bright. So if you're going to use more exposure time, you're going to burn the area under the sun. If you close the shutter, you have very dark areas where you have the shade. So in the processing of the HDR, you can't use just the regular gamma, because if you're using just the regular gamma, especially in Bayer images, which has a higher throughput, each pixel needs to be accelerated, but not according to its value, because then if you do it according to its value, you destroy the contrast. You want that acceleration to be according to the scenario and the area around you. And what you see here on the right-hand side is that an HDR that is taking in account the area, taking in account the coloring to make sure that we keep the coloring, and also to look at doing some edge enhancement or having an option for edge enhancements as well. If you have sharp eyes, you may be able to see some elements of edge enhancement as well, to have, again, better recognition or better detection. And here's the advantage of doing that through the FPGA. On the left-hand side, we see a large computer needs to do the processing, and it's very limited with performance. So you can see on the where the arrow shows you a difference in the edging and analyzing the edges, and coloring when it gets in and out the shade. On the FPGA, we can run the HDR, the gamma, the white balance, and compression all in the same flow and make it simpler. And the reason is because in the FPGA, you can run as much as logic as you want, so we can add more complex algorithms to develop the algorithm compared to the software, and that's why it's better thing. And definitely we can run that on speeds faster than gigapixels per second, which is today demanding. Now, when we want to go from the concept to market, as Oliver said, it's very important to understand. Using modules absolutely helps, I agree. Then you have the design time, you have the coding, you have the compiling, you have the testing, you have validating, and in many cases, you do need to have improvements. You need to have a cycle and cycle and cycle. So what we found out is something amazing. We found out that when you're developing something complex, such as quality HDR, or quality compression, or other high-level algorithms of detection, you put time on the coding, you put time on compiling, but the most time that you put is in testing and validating, and even more than that, on the improvements that you want to do, because the improvements are small changes that you need to run through many, many videos or many, many images. And if you run those in software, the time of the validation and improving is slower. So we are offering an example of having a camera simulator that runs videos as you want into the images under the development, and then you can access directly from the host to your application and send it to a frame grabber to see the results on the screen. And finally, you can have all the features of acceleration and so on with a very small computers that we can demo on our booth D20 over here. So first of all, everyone is welcome. And the other thing is, if you have any questions, I would be more than welcome to answer you.
Thank you. Thank you, Ruben. Questions? I could allow one question. No?
Okay.
You covered it all, Ruben.
Okay, thank you very much.
My next speaker is Frederik Schönebeck from the company Framos. And Frederik is going to talk about fundamental building blocks for successful vision AI systems. I'm not sure if the live stream is already available, so hence let's wait 2 minutes. 2 minutes, and I'll do some promotion. Later on, I mean, all the sessions are great here at the Industrial Vision booth, Industrial Vision Days. Later on, there's going to be a panel discussion starting at 3 on generative AI. Dream or coming true? What's in it for machine vision? So I guess that's very exciting, starting at 3 o'clock. And of course, one of my favorite sessions is always the vision pitch-up session. Mm-hmm. Tomorrow morning, last session of the vision startup pitches, starting tomorrow at 9:15. However, time is now, I think, running. So let's start with our next presentation. As I said, Frederik from Framos, about fundamental building blocks for successful vision AI systems. Okay, Frederik.
Thank you very much. Let's see if we... there we go. Hello, I'm Frederik. Welcome all. I'd like to talk about vision AI systems, specifically more embedded vision systems, and what the fundamental building blocks are, what you need to do in order to be successful. A quick sort of introduction on why we at Framos feel that this is important. I found this figure which sort of predicts the growth that is expected globally in the AI-powered camera market. And you see that it's quite an exponential growth, quite impressive. That's sort of expected. And it's certainly because there are these huge advancements in compute power on the edge. Just like the other two speakers already mentioned, there is lots of compute power available. There were some recent claims that maybe there is some slowing down expected. There is Jensen Huang from NVIDIA claiming that maybe Moore's law is dead. There is, I think, different perspectives to that, but I think we all agree that we can still expect huge advancements in the compute power, and people are creative. They want to apply this compute power, and they think of AI-driven devices where they can really generate value by using AI models based on vision technology. Now, what does a typical embedded vision setup look like that sort of we are seeing in the market? It is consisting of sort of a central compute device, often SoC-based, which also has an image signal processor included. And then there are sort of optical sensor modules that are really sort of integrating directly and natively, often through the MIPI interface, into this central processing platform. Keep in mind, that's sort of the target platform that I have, that I use throughout this presentation. Now, in this talk, I'd like to highlight 4 of the main building blocks and their associated challenges when people like you want to design your next generation vision system. The first building block is certainly the image sensor. That's also where we come from at Framos. We are very good at understanding image sensors. And one of the typical challenges we see in the market is that people ask themselves, how can I truly sort of assess the image quality of the sensor itself? What are proper quality metrics that I can use to optimize my camera design? And I will speak about this later in the presentation. Another challenge is around the optics of the system. Typically, each image sensor is paired with a lens. And the question that we always see in the market is, how do I actually choose my lens subsystem such that I can truly maximize the image quality at the end? Another challenge which I will address in my presentation. There's a third one, the third main building block in any vision system, the image signal processor. It's usually a block in the SoC. Sometimes you can also do it yourself in FPGA, like we just learned. But typically, there is an existing pipeline that people would like to control in order to, well, tune the look and feel of the image and really make it suitable for the application. And the question is how to do that. Now, these are the 3 main building blocks, but I mentioned there's a fourth. And the fourth one is certainly, in my opinion, the most underrated one, especially when it comes to larger volumes, and that is production. How am I actually able to measure and maintain my quality, and at the end also my image quality, throughout larger production volumes? That's the fourth building block I'd like to address in my presentation. Let's start with the sensor. Sensor characteristics are sort of noise, sensitivity, dynamic range. There's a whole lot of different sensor characteristics. And typically, when people start, they look at the data sheet. They are intrigued by all the values they see, super low noise, super high sensitivity. They make their design of their camera, and they are, as you may see in the sort of the top picture, they are disappointed because they do see lots of noise. And this is where then typically you need to optimize. You need to optimize your electrical design, and there's a very powerful tool you can use, and that's the so-called EMVA 1288 standard that we also use internally when we do our design-ins. It's a standard which allows you to characterize sensor characteristics in a very standardized way, and with that you can truly understand how good your design is. I can only recommend, in case you do your own camera designs, that you really try to implement that standard in your daily operations. It will definitely improve your outcome. Second challenge that we hear, lens selection. Lens is, and I think typically people sort of often underestimate this, lens is an analog device. It's not digital. It's good or bad. You get all the gray values in between. And it truly depends also on the production quality of the lens itself. And so with a lens, there are so many things you need to watch out for when making the right selection. I sort of list out just a few basic ones. Certainly the image circle of the lens needs to match the sensor. Then also a very important one, the lens itself has a resolving power, and that needs to fundamentally match up with the pixel pitch of the sensor. If you get this wrong, your image performance will suffer, and it may even suffer dramatically. Then a lens also has an F number that typically controls not only the amount of light, but also the depth of field. So in case you have a depth of field sensitive application, something to pay attention to. A fourth one here, depth of focus, truly underestimated very, very often. So the lens itself is not always producing only a single sharp image plane where you then sort of position your sensor. Typically, the wavefront of the lens, depending on the build quality, is sort of distorted. And you need to account for that when focusing, so when moving your image sensor to the right position to get a sharp image. And this needs to be taken into account when you do your assembly, and especially when you go to higher volumes, when you want to maintain a certain consistency throughout larger volumes. So that's definitely something you should have on your radar. And then the last one, there is also one fundamental characteristic, which is called chief ray angle, where a sensor has a certain chief ray angle and the lens. And in case they don't match up, I actually brought a nice image. You may see here in the projector that in the center of the image you get some purple tint. So really it's a color gradient, and that is because the coupling of the light rays into the photodiode of the pixel depends on where you are on the sensor. It is different in the center as compared to the outer pixels, and there you may lose differentially different wavelengths, and that ultimately results into a color gradient, and it's almost impossible to really calibrate this out in post-processing. So these are some of the fundamental things you need to do when selecting your lens and pairing it with your sensor. There is a white paper we have, and also you can, of course, come to our booth anytime to learn more about how you best do that. This was the lens selection. There's the ISP, which I mentioned as a third building block. The ISP sort of converts the raw data, gray values coming from the sensor, into an image that is actually pleasant to our eyes. And if you don't do that well, you may get something like this. You do see some colors, so some color conversion has happened in debayering, but it doesn't look very crispy. There's maybe a green tint in this specific case, so it's not necessarily something you would like to show into the field to your customers. And that's why you need an ISP, and you need a proper ISP that can allow for different steps in the image pipeline. For instance, black level and defect correction. Then, of course, color reproduction, white balancing. I mean, really, we now list here 7, but actually there are pipelines that are even much more sophisticated than just these 7 steps. But you need to be able to really control, to a certain extent, all of these steps to truly get an output image that is somewhat pleasant to your eyes. And if you do that, if you really tune this properly, then you end up with something like this, which is, well, a lot more pleasant. You can feed this back into your central processor. You can start with your application development now based on this image and not based on something that looks bad. Image processing tuning is a little bit of an art even. I mean, at the end, it's all math. But since these ISPs are often closed and not really publicly documented, you need to work yourself around this, often by experimenting, but then also what is really a requirement is that you have a very good relationship with the provider of the ISP, and that's also where companies like Framos, but also others can help to make this connection and truly get you the image that you need. Next use case, or next challenge, last challenge, production quality. So at the end, you select your sensor, you select your lens, you do your ISP tuning, you get a good-looking image, but this is only maybe for a single piece or 10 pieces. You like what you see, but you then need to ensure that you can reproduce this as higher volumes. Not sure what your application may require, maybe several hundreds, thousands. Some customers that we do business with even have hundreds of thousands. And there you need to ensure that you can maintain and monitor quality throughout larger batches. We do all our production in-house, and we are a vision-centric company. So we don't do general purpose system manufacturing. We only do vision-centric manufacturing. And in our production workflow, we measure the essential image quality characteristics for each piece. And what I show here is sort of a distribution of sharpness values for, I don't know, I think this was a 10,000 piece batch. You can see it's sort of a regular, normal Gaussian distribution, just as you would expect. There is production tolerances, but then together with our customers, we can sort of define cutoff criteria. What is considered good enough? What is considered not good enough? We can really nail this down. We do software-assisted production, so we have those characteristics measured for each device, and then we can really differentiate between OK and not OK. It will affect the yield, it will affect the cost, and we will always work with our customers to optimize this, but this is just a fundamental process you need to have in place in order to optimize your system performance. Now, these were the 4 big topics I wanted to show to you. I hope you found them valuable. What we did at Framos is that we sort of tried to productize all that into a family of camera modules, our so-called FSM Go. So what you see there is a platform. So again, we also take a modular approach, which I think today in this diversity of applications we see is the only viable approach you can actually take. But the way how this platform is sort of designed is that you can pick your sensor, you can pick different lenses, all of these are pre-qualified, you can pick different ISP tunings, and the manufacturing process is optimized in a way that you can, it doesn't matter whether you just order 1 piece or you order 10,000 pieces, it's all already streamlined to ensure that you get the product you need to be successful. And with that, my presentation ends. I'd like to thank you. I invite you over to our booth in Hall 10, right in the center. I think it's E54. We can continue with our discussions in case you have any questions. And very important, I was just now presenting an overview. We have four of my colleagues who are the true experts actually provide in-depth presentations of these topics that I mentioned here. So you please come to our booth and get registered and try to get a seat in one of these presentations. Very insightful. I can only invite you. And now thanks for your attention and your time.
Thank you, Frederik from Framos, also for the invitation. I mean, this is why we are at Vision. We want to discuss with experts about vision technologies, about applications, about the way to go, about the future.
Yes.
So please make the most
Let's
out
connect.
of your time here. Yeah, we still have some time, so if there is one question you would like to raise here, feel free so. I don't see any hands, so therefore, please go to the Framos booth, go to the HEMA Electronics booth, go to the Gidel booth, and talk to the presenters directly there. Okay, thank you.
Thank you very much.